External and Implantable Defibrillators by Team 6, consisting of Michael Thyssen, Fashoy Risk, Abdullah Shanak, and Abanub Eskander. Background. Until 1950, ventricular fibrillation was only treated with drug therapy. Then in 1956, cardiologist Paul Zoy used an electrical shock from an AC outlet, but this method was untested and unsafe. In 1959, Bernard Lown demonstrated that AC was injurious to the heart and lethal. In 1961, he also proved that DC waveform consistently reversed fibrillation without injury. He went on to experiment new ways to treat non-life-threatening tachycardias. The normal heart rate is under 100 beats per minute and with a pulsating waveform. Ventricular fibrillation is characterized by a fast and continuous waveform. The input signal to the defibrillator is the heart rate itself. The ICD senses the heart's electrical activity and continuously comparing the heart rate with a physician's programmed rate threshold. The ICD has many components in it, such as the fibrillation sensing circuits, the battery, high voltage generator, and defibrillating capacitors, and among other components. When there is an abnormal rhythm detected by the fibrillation sensing circuits, the fibrillating capacitor is charged with high voltage, then the capacitor is discharged to restore the normal rhythm to the heart. The voltage release is the output. There are two types of defibrillators, implantable and external. The implantable defibrillators are placed under the skin, near the chest, and the leads are inserted into the heart through the blood vessels. The DC sensing circuits detect abnormal heart rhythm, and they deliver an electrical shock to restore normal heartbeat when the irregular rhythm happens. They do not restart the heart, they only reset it. External defibrillators are either AC or DC, can be portable. They are placed in hospitals or public places and readily available when needed. They use pads placed on the patient's chest. These pads are both sensing and electrical shock circuits. They restore the normal heartbeat when an abnormal rhythm occurs and resets the heart, does not restart the heart. Basic electrical circuitry block diagram. For an internal ICD, you have the leads, pulse generator, battery, capacitor, and central processing unit. Leads are electrode tip set of wires placed in the chambers of the heart, and they use to sense the heart's electrical activity as well as deliver the electrical impulses or shock. The pulse generator houses the batteries, CPU, as well as other circuitry components. The battery serves as the powerhouse of the device but cannot deliver high energy shocks. That's where the capacitor comes in, which is charged through the charging circuit and the battery and provides a high energy shock by releasing all stored energy instantly. The central processing unit serves as a control center as well as data storage and maintains a log of electrical activity and details of the arrhythmia episodes and the shocks delivered. The external defibrillator charging circuit comprises of a DC supply and series R1 resistor, which limits the charging current and determines the charging time. Depending on the capacitor's value and the required shock energy, the supply may well need to provide upward of 2,000 and as high as 5,000 volts. The potential divider formed by R2 and R3 monitor the capacitor voltage and provide a lower voltage signal that is used to disconnect the supply once the required charge level is reached. Discharge of the inductor is a heavily dampened pulse that typically delivers 100 joules of energy over a period of around 5 milliseconds. The system shown provides a fixed polarity pulse, whereas most defibrillators designed now have a biphasic pulse so as to reverse the polarity of alternate pulses. Biphasic defibrillators achieve a higher success rate and operate at reduced energy levels. The performance requirements of the resistors used in AEDs, including the associated cardiac monitor circuits, are quite demanding and must be able to withstand high voltages, but R1 is carrying the charging current, so while its value and hence accuracy are not important, it will probably need to be capable of dissipating around 10 watts of power. The ratio of the values of R2 and R3 might be in the order of 500 to 1 to divide a supply voltage of say 1000 volts down to a level of 2 volts, compatible with the comparator input range of a typical microcontroller. Hence R2, where 10 megaohms, and R3 would need to be around 20 megaohms. The temperature and stability and voltage linearity are critical performance characteristics divided by the parameters set. Principles of a defibrillator. Energy is stored in a capacitor and delivered at a relatively rapid rate to the patient's chest. The discharge of the capacitor's energy is proportional to the resistance through the patient. The discharge resistance, which the patient represents, is approximately 50 to 100 ohms for a typical electrode size of 80 centimeters squared. During charge, when V equals E, the current ceases to flow and the capacitor is fully charged. The energy delivered may be calculated from energy equals 1/2 stored charge times potential. So for example, energy equals QV divided by 2. The apparent loss of half of the stored charge on the discharge is due to the circuit's resistance, radiation, and the arcing of switch contacts. Different types of waveforms used. Monophasic, which delivers current in one polarity, shows the rate at which current pulse decreases to 0. In biphasic, delivery of the current flow is in a positive direction for a specified time, then reverses for a duration of the discharge. This waveform is called the lone waveform and is approximately 10 milliseconds. Timing of the electrical discharge outside the heart's brief vulnerable period of 0.03 seconds in duration prevented ventricular defibrillation or sudden cardiac death. In AC charging circuits, they are used in larger machines, can be plugged into the wall, they're easy to charge, can charge to a higher rate settings for discharge. They're good for hospitals and stationary settings, but not very mobile. In DC charging circuits, which have batteries, they're smaller machines, more mobile, but the battery limits the deliverable charge to the patient. In voltage-controlled defibrillation, voltage would have to be too high, transformers and capacitors too large and too heavy, which would end up having large machines. In current-controlled, the current is allowed to change for preset values and can be used in biphasic defibrillation, and both phases can be current-controlled. This is believed to be the best choice for future designs. Modern challenges and solutions. There is a fairly new implantable defibrillator developed in 2008 by Cameron Health in San Clemente, California. This new device shocks the heart from outside the heart, which is unlike any of the other implantable defibrillators prior to this device, all of which shock from within the body. The device created by Cameron only has a 5-year battery life. They only provide 80 joules per shock, which is higher than the previous defibrillators, but is still insufficient for many patients with weak hearts. Solutions are creating a self-sustaining battery, a motion charging battery being implemented in the design of this device could potentially wipe out the need for changing out of the batteries. Also, a self-sustaining battery or wireless charging would allow for more joules to be given per shock without the worry for draining the batteries. Thank you. Thank you.